Good morning, students. Let us discuss the wave equation. We are having two types of derivations, that is called as wave equation and heat equation. So this is very important, and their solution is also there. Okay. So what we are going to do is that today we derive an one-dimensional wave equation, which is due to the transverse vibrations. It is due to the transverse vibration of the stretched rings. We also discuss the solution of this wave equation. Okay, so let us go for this one. The derivation is like this: derivation of one-dimensional wave equation. The question will be asked in the examination like this: derive one-dimensional wave equation in standard form, or derive a one-dimensional wave equation of the form dou square u upon dou t square is equal to c square into dou square u upon dou x square. This is equation of the wave. Okay, so you have to derive this one. To derive this one, let us go for some important physics part that you have to consider one flexible string that stretched between two fixed points at the distance of L apart. Okay, let rho be the small, let rho be the mass per unit length of the string. Now to derive this one, let us assume some following conditions. That first condition is that the tension should be ignored. Okay, the tension T of the string is some same throughout. Same means if you stretch a string, this is a string, this is a string. If you stretch this one, the tension throughout this one you cannot change. You just keep it as it is. Tension means you stretched it. So therefore it is the first condition. So the effect of the gravity can be ignored due to the large tension of T. That means if you stretch this one, the gravity it becomes a zero. It should be ignored here. The motion of the string is a small. The motion of the string is small here. Stretched vibrations are there. If you stretch this one, some small vibration will happen here. So for this one, let us discuss the diagram is also like this. So you take one string here, you take a string here, and you pull here, and give the tension from T1 and give the tension to the T2. The small distance is up here. So let us discuss this one by the small points. Let us consider the force acting on a small element AB of length dx. This is a length AB and the distance is delta x here. Okay, let T1 and T2 be the tension at the point A and B. This is tension A, this is tension B. If you stretch this one, tension will happen along A and along B. Okay, since there is no motion in the horizontal direction, only we are giving the tension to the vertically. Therefore there is no tension in the horizontal. So therefore the horizontal components T1 and T2 must cancel each other. There is no horizontal direction. Now let us go for if you know there is no horizontal direction, means T1 cos alpha and T2 cos beta. Therefore this is an angle alpha, this is an angle beta. Okay, that becomes a tension, that is total tension it becomes. Okay, call it as equation 1. Now where alpha and beta are the two angles made by the T1 and T2 with the horizontal. Okay, so let us go for this one. Vertical components of the tensions are minus T1 alpha sine alpha and T2 sine beta, where the negative signs is because the T1 is directed downwards. Hence the resultant force acting vertically upwards is T2 sine beta minus T2 sine alpha. What they are going to tell is that this T1 is moving downwards, okay, and T2 is moving upwards. So this becomes a negative sign and this is a positive sign. They are treating only on a vertical direction. So therefore total resultant force is given as T2, you have to take here sine beta, and T1 sine alpha minus, that is T2 sine beta minus T1 sine alpha angle becomes. So therefore it becomes like this. Okay, so then applying the Newton's second law of motion, the Newton's second law is force is equal to mass into acceleration. So force is given as, this is total force.